Welcome back. We do still need to finish up number one. We had some technical difficulties there, and the difficulty started when we were looking at determining what type of bond it would try to be. We have silicon dioxide, so we have oxygen, which is 3,5, bonded to the silicone, which is 1,8. So we'll put those numbers on our paper. Oxygen's 3,5, silicone's 1,8. The difference is 1,7. That would try to be a polar bond if it could. They would try to be polar bonds if they could. So we can circle polar bonds. Now, what is the point of circling polar bonds? Really nothing. This molecule cannot be a polar molecule. We've already established that this molecule is symmetrical. There are no lone pairs. So the two oxygens are trying to pull the electrons, but they cancel each other out. So the bonds would try to be polar. But the molecule can't be polar. The molecule cannot be polar here. There is no way it can be polar. It's not polar. Couldn't be. So, once again, that is only because the molecule is symmetrical. The only way we can get a polar molecule is if the molecule has lone pairs or different types of atoms, as it says here. If there are lone pairs, the lone pairs do not equal 0. And if there are different types of atoms, or if there's different types of atoms, and the molecule has to have polar bonds. So the only way we can get the polar molecule is polar bonds and asymmetrical. That's the only way we can get through that avenue. So we've got a nonpolar molecule here. And now we can move on to the very next problem. The next problem is asking us to determine the shape for phosgene. COCl2, sometimes called carbonyl dichloride. We have one carbon with 4 electrons. We have one oxygen with 6 electrons. We have 2 chlorines with 7 electrons each for 14. So the total number of electrons we have to work with here is 24. So we can see with 24 electrons to work with, carbon has 4, needs 4 more to get 8. So it will be our atom in the middle. It'll be our central atom. And we will now surround it with 8. We have our 8 electrons around carbon, and it's now time to attach the 2 chlorines to the molecule. And we will also attach the oxygen to a molecule, and they can be attached wherever there is a lone pair. So we've got those attached, chlorines on there, the oxygen's on there. And now what we'll do next is surround the oxygen and the 2 chlorines with 8. So we can take a look here. The chlorines and the oxygens all have 8 around them. So that's 8, 16, 24, 25, 26 electrons on this diagram. And we are only allowed 24. So we'll need to erase 2. The rules are we can erase 2 from any atom that is attached to another atom that has 2 that it can donate to the bond to make up for the ones that you erased. Now, in this case, we want to strategize, because if I erase from either of the chlorines, the carbon is going to have to put 2 into the bond, and that would give chlorine a double bond. Chlorine prefers single bonds if it can make them. Chlorine's very versatile, but it would prefer single bonds on this molecule because it could make them. So with that said, I could erase a pair from an oxygen and put the pair from the carbon in, or I could erase a pair from the carbon and put a pair from the oxygen into the bond, causing a double bond between the carbon and the oxygen. Oxygen's good with double bonds. Oxygen starts with 6. It needs 2 bonds to get 8. A double bond will work just fine. So I think we're going to go ahead and erase this pair underneath carbon right here. We'll get rid of this pair right here. And we will move these 2 into the bond, creating a double bond. That gets us down to the numbers of electrons we are supposed to have: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have a double bonded to the carbon to the oxygen. We have a single bond to each of the chlorines. Every atom here on this molecule has the 8 they need for the octet rule. So we can go ahead and erase shared pairs with lines to turn it into a Lewis structure. Now that we have our Lewis structure, we can now begin to interpret the Lewis structure using the valence shell electron pair repulsion theory to try to determine some of the important aspects of this molecule. So let's begin. First thing we need to do is count the total things. It says start right here. It says count the total things, which we call the steric number surrounding the carbon. Remember, we count total things. That would be atoms on the central atom or lone pairs on the central atom. We can see carbon has bonded to 3 atoms, the oxygen, the chlorine, and the chlorine. That is 3 atoms it's bonded to, and there are no lone pairs on the carbon. So we can go ahead and put a 3 right here for our total things. That is our total number of things around there on that central atom. And we know that those total things are 3 bonded atoms and no lone pairs. 3 bonded atoms and no lone pairs for a total of 3 things. We can already guess what the shape is by knowing that there's 3 total things on here. What is the shape when there's 3 total things on here? There's the 3. That would make it trigonal, planar. We can see our shape sheet would take us right there. When there's 3 things around the central atom, it is in the trigonal planar family. And when there are 3 things and no lone pairs, it is the trigonal planar molecule. That's the actual shape, is trigonal planar. So we can go ahead and circle those. So we see here on our shape sheet, we had 3 bonded atoms and 0 lone pairs. That's a 3, 0. That's trigonal planar. When we have a planar atom, there really isn't an axial or equatorial plane. So when we have those 3 atoms and no lone pairs, we know that the bonding angle, as it would say right here, is 360. Those 3 atoms spread out evenly throughout the plane. So here's the 3, 0, trigonal planar. The bond angles are 120. It's symmetrical. Our shape formula is AB3, which is the same as AB3E0. All of that's on the shape sheet, and we can go ahead and circle those things on our problem. Well, I didn't mean circle those. The angles are going to be 120 because we have the 3 atoms distributed evenly in a plane. So a circle is 360. You divide that by 3. The angles are 120. The shape formula is AB3E0. So here we go. We've got to take a look at where we're going on the shape sheet here. All right, I'm coming out of here. E equals 0. E does equal 0, so I'm thinking I'm going down this way. And it would be symmetrical if all the atoms are the same. So when E equals 0 and all the atoms are the same surrounding the central atom, then it's symmetrical. However, when we look at this molecule right up here, we have a carbon with 2 chlorines and an oxygen. The atoms are not the same. The atoms are different. If the atoms are different, it doesn't matter how many lone pairs there are on the central atom. So from different, we come down, and it'll make this molecule automatically asymmetrical. Now we can see we got to asymmetrical. It says if there are different atoms surrounding the central atom, it is automatically asymmetrical. Or if you have lone pairs, if your E is not equal to 0, it's asymmetrical. That's 2 ways we can get to asymmetrical. That doesn't mean the molecule, if it's asymmetrical, is automatically a polar molecule. It doesn't mean it's automatically polar. If it's asymmetrical, the way we get to be polar is if it has polar bonds. We probably wouldn't even need to really figure out the electronegativities of this thing. They're figured out for us already on here. Carbon's 2,5, chlorine's 3,0. 3,0 minus 2,5 is 0.5. That's polar. The carbon and oxygen double bond there. That's why there's 2 lines there. The carbon double bonded to the oxygen. The difference there, 3,5 for oxygen, 2,5 for the carbon. The difference is 1,0. That's polar. We do have polar bonds on this molecule. You probably wouldn't need to use the electronegativity table to do it because oxygen sharing with anything is automatically polar because oxygen is 3,5. The next highest is 3,0. That's polar. Also, the next highest is fluorine. It's 4,0. So oxygen sharing with anything is polar. So I'm going to go ahead and circle polar right here. I've got polar bonds. If it's asymmetrical and it's polar, the molecule is polar, provided for sure that it's not an ionic molecule. So the strongest forces we would see on this molecule would be dipole-dipole forces. There would be partial positive areas and partial negative areas on this molecule. Partial negative on the oxygen, that would be one of the strongest partial negatives. Then each of the chlorines would have potentially have a partial negative, except they're poling directly opposite each other. So the chlorines would tend to cancel each other out, and it looks like it would be poling opposite, but remember, this is a two-dimensional drawing. The chlorines are actually at a 120 angle, so they wouldn't cancel out in this case. It's a 120 angle. They wouldn't be pulling opposite each other. This line would be coming down here. This line would be coming down here if we were drawing it three-dimensionally. That means the chlorines would have partial negatives, leaving the carbon in the middle partial positive.